let's get started. Okay, so here's where we're at. I say the word math, okay? We've also said the word numeracy, which is a fancy word, right? Which, if we take it, really is just about numbers, right? And math is short for mathematics, blah, blah, blah. But we started with just the why question. Like, why should we even bother, right? And I tried to show you guys through career planning activities, through examining how you graduate, that the reality is that studying math is important for that purpose. And then our first unit, and in general the way you study math, is with what is sometimes just called arithmetic. Arithmetic, okay? Which is your basic math, right? First learning to count, then learning to add, then learning to subtract or take away, then learning to multiply, and then divide. And then from there we expanded up to the point where you need to have a level of arithmetic that's ready to do the grade 9 math, which included things like fractions, negative numbers, order of operations, decimals, and percentages. So arithmetic went from the basics, which was the whole adding, subtracting, etc., to now things like I said, the fractions, the negatives, the order of operations, the decimals, and the percentages, all that stuff. We're now done that, okay? How much effort you put into that and how ready you are to move away from it, that's individual. We looked at that yesterday, sort of where you fall in terms of statistical data. But where does it go next? Okay? Where does your learning in math go to? Let's go to the end game. Let's go to the end of all your studies. At the end of high school, at the end of wherever you want to stop learning math, eventually you're going to use math in some way in the real world. But you may not call it that anymore. You need to turn what is happening in school into something that's happening in real life. Okay? And we need to put something in the middle. Okay? Math has to become somehow more real to you. And part of that, I hope, is what I'm going to try to address today is where is this sort of where math gets more realistic? And in some ways, that turned into a spot where you guys maybe lost your connection with math. Maybe it got so different that it didn't seem like math anymore. And that's kind of what I want to talk about today in part 1 of this new unit, Abstract Math. Okay, and we're going to take a look at the traditional way that's described as algebra. Okay, but before we start with that, let's just turn to the word reason. Okay? The word reason and the ability to reason is what defines us as humans, right? This is what makes us, say, better than some little piece of chemical on a piece of glass. The ability to use reasoning is a crucial part of our lives. I mean, the fact that you were able to use reasoning shows that you were able to make it here today to school and put on clothes and eat and survive. That's all part of reasoning. Now, reasoning is also part of like solving mysteries. So who, in your opinion, is the most famous mystery solver in all of literature? Scooby-Doo? Who else? Indiana Jones? Anyone else? I'll throw out Batman. He's been described as the world's greatest detective. Sherlock Holmes? Well, let's go with that example. Sherlock Holmes. Sherlock Holmes prided himself on his ability to use reason to solve crimes. Here's an example. A police officer asked Sherlock Holmes if there was anything about the crime that he just examined that struck him as significant. And Sherlock Holmes said, yep, it was the dog in the nighttime. And the officer said, well, why is that significant? The dog didn't do anything. The dog did nothing. All the witnesses say that the dog didn't even bark. And Holmes said, that's what's significant. Now, why Sherlock Holmes thought that was significant was part of his reason. Here's the way he summarized it. He said, well, watchdogs bark at strangers. That's a true statement. He said, the watchdog did not bark at the thief. So you know what? The thief was not a stranger. to this place that was robbed. And that was basic logic. And what that is often called, there's a fancy name for this type of logic called a syllogism. It's a basic building block of philosophy, which is the study of why we are what we are. But it's also just basically, it just makes sense. Once you think about it, it makes sense. And that's what math tries to do. It tries to use reason as a primary tool to just make sense of things. But at some point in studying math, you probably made the statement, it doesn't make sense anymore. Okay? At some point, your math made sense, and then at another point, it didn't make sense. And that's where you lost a connection to mathematics. So now we're going to move beyond the arithmetic phase into stuff a little more abstract. Okay. And I've used these words before. I've used the word leap of abstraction in this class before. It was when math was made sense by things like saying 2 apples, and I give you 2 more apples, you now get 4 apples. And then it moved from that to 2 plus 2 equals 4. And even that is an abstract statement, right? If you show this, 2 plus 2 equals 4, to like a 1-year-old, they may not be able to understand what it means. Whereas they might be able to understand if I give you these 2 toys and I give you 2 more toys, that they'd have 4 toys. They might understand that. And math gets more and more abstract. I mean, this is an example of a very hard grade 9 math problem right here. The square root of 2x cubed minus 1/3 6 times y. That's tricky, okay? But it's at a level that could possibly, now I'm not saying it's a typical question, but it's not, anything in there is not impossible to a grade 9 math student if they understand the level of abstraction that's going on there. And at some point, possibly you lost that connection. So losing that ability to leap is usually just summarized as, I don't get it, right? People make that statement, I don't get it, right? So, but you get reasoning. Like if you walk outside in the morning and see the sidewalk outside your house is wet, you're probably going to make a reasonable conclusion that it probably rained last night. That's good reasoning. That makes sense. So why would something like this not make sense? Oops. Is because at some point you lost that connection and the math became too abstract for you. So as we move into math that starts down that path, I want to make sure that you don't lose that connection. Okay. Now, in some math textbooks, they put it out different ways, but maybe it could be summarized in a simpler way, right? Like, let's say you have some sort of problem, okay? So let me try and draw it out, okay? So somehow, you have a problem, okay? Now, that problem might have been told to you. Someone said, hey, Solon, and they described a problem to you. So someone might have told you the problem, or let's say you're in a math class. Maybe someone wrote it down for you. They wrote down a problem. So this is really just language, right? Whether it's someone speaking it or whether you're reading it, that's one way you'd get to the problem, is someone will tell you the problem. Now, the next part is you got to solve it, right? So you've got this problem in front of you. So you've got it written down. Someone told it to you or it's written down. You've got to try to interpret that problem and try to make sense out of it, okay? What this might mean is you will use another part of language. You will write stuff down. But you know what? Before you do that, chances are you might visualize it. You might think about what it looks like. And that often makes problems make more sense to you. If you can kind of imagine 2 apples, you can kind of visualize 2 apples. But then you go and write it down, and you're writing down using symbols, right? Things like the number 2 and a plus sign, and another number 2 and an equal sign. Those are symbols. So these 3 things, writing stuff down, you reading it, you visualizing it, all of these things are connected to you solving the problem. And in most math textbooks, that's often the way it's described. As a matter of fact, let me show you the visual I have. Oops. This is actually from a math textbook that in order to do math, you should be able to write it out using math symbols, like write 2 plus 2. You should be able to visualize it. So you should be able to draw pictures or things like pictures, like a chart or something like that. And you should be able to understand it in words. You should be able to describe the problem to someone in words, either writing it out in words or saying it out loud using your voice. And that's what generally math becomes. It becomes this ability to translate problems in these three ways. Now here's an example of stuff you should know. Here's some symbols that you should already know, right? That these symbols, that one, these two, and that one, represent something, okay? They represent, here's an example of them in use. 3 plus 1, 3 minus 1, 2 times 3, 4 divided by 2. But you should also know that these have words that are associated with them. Sometimes those words are confusing. Sometimes, like for example, this one has several words. It can mean multiply. It can also mean times, multiplication, or even the word product. Not used as much, but those words all mean what this symbol represents. These ones as well. This can mean adding or addition or sum, or even just the words more than is what that means. If I say, what's 3 more than 5, you'd go, well, it's 8. Well, how did you do that? Well, you went 5 plus 8, right? Whoops. So these are symbols that already make math a little more abstract. But I think, and you guys have demonstrated, that you've mastered these. So now moving on, even numbers themselves are abstract. So math tries to take this world of abstract concepts and get very precise about the language it uses. But let's focus on what it's being used for. Math is really being used to solve problems, because that's practical. That's the practical end of math, is it using it to solve actual real-world problems. That's the thing I was talking about back here. We want to use math to solve problems in real life. We've reached the end of the simple arithmetic, and some of it wasn't that simple because we got a little more complex with it. But now we've got to move into a place where math becomes a type of problem solving that makes more realistic things happen. So let's take a look at problem solving, okay? So this can be related to things like word problems, but I'm not going to deal with word problems today. But what I do want to use is using math in this sort of practical way. And this relates to other subjects, right? I mean, if you can use math in a practical way, you can do science. Science is related to math being used in a sort of a realistic way. Construction is math being used in a practical way. Banking and baking is math being used in a practical way. Trust me, if you don't follow the specific instructions on a recipe, your cake's going to turn out terrible in baking. If you don't measure when you're doing construction and use math in a practical way, what you're constructing is going to not work, okay? So what I'm going to do is I'm going to give you today a 5-step way to solve any problem, anytime, anywhere. That's a big claim on my part, but I'm going to try. 5 steps to solve any problem, and it's not about math. It's just in general, okay? It could be. Well, I didn't say it was about math. Just problems in general. So the problem of how to get a date, the problem of how to get a job, or what job should I get, or where should I live, or all these are problems. I'm going to give you 5 steps to solving all of those problems. Sure. Now here's the way I've defined math so far to you guys. I said, let's break it down to simple terms. Language, and if you look at those little books I gave you, that's what it was about. Here are the words you need to know. And then what was the second part? Does anyone know? Method, which was the step-by-step. But now we're going to take those and apply them to problem solving. Okay, in general, not necessarily about math. Okay, here are the 5 steps. Step 1, this is the most important step. What is your problem? Right? That's the answer we often give to people. What's your problem? But we have to define the problem. You can't solve a problem unless you know what it's actually asking. If you can't do step 1, you're never going to get to the other steps. So if a teacher says, here's an essay you're supposed to write, you better know what that actually means. You better know what the heck you're supposed to be solving. If you're given a project to do in social studies, you need to know exactly what you're doing before you go further at all. If you're handed a math question by a math teacher, you better know what that problem is actually asking you. Define the problem. Step 2, you've seen this before. Come up with find a method. Now the method depends on the problem, right? If I give you a fraction problem, there's different methods you can use. If I give you an essay, you're not going to use a math method, you're going to use some other method. So the method relates to that. So that's why I'm just going to say method, which is just what are the steps I'm going to take. Step 3 is easy. Once you've found a method, use it. Use the method. So for example, if it's a fraction problem and it was 2 fractions being multiplied, you'd go, okay, well here's what I got to do. I got to multiply the top, multiply the bottom. Then go ahead and do that. Go ahead and do the actual math. Step 4, now you got your solution. That's the answer, step 4. And then the 5th step, which is super important, check it. Check it over. 5 steps solves any problem. You actually may notice that I actually have this up as a poster in here, this 5-step problem solving. And I don't have that with the word math over top of it. I use those 5 steps for all the courses I teach. These are the 5 steps to solving any problem. Because is that not what education is? It's about solving problems? All right. So when you do step 1, here's some of the tips I'd give you. Look at the problem carefully. Like actually figure out what you're looking at. What am I trying to find? What do I know? What don't I know? What do I still need to find out? Possibly restating it. Like sometimes when you're given a problem, you have to reword it to make sense to you. Sometimes you can ignore certain words when you look at the problem. Make sure you understand the situation, what the question's actually asking, and you might even want to draw a picture to help you really understand what the problem is. Depends on the level of the problem. Then you go to step 2. What's the method? You might know the method. You go, oh, well, this is art class and I've been given a problem. I need some paper and pencil. So the method is I got to get those supplies. What do I still need to do? Do I need any specific techniques? Maybe I need to look something up on the internet or open up a textbook that will help me get the techniques. Or like in our class, maybe I'll grab that little guidebook that Walk's made for me. That might help me get the method. And you know what? If you can't think of a method, then invent one. Because maybe the problem is not happening in school. Maybe the problem is I need to find a job and you need to find a way that works for you, a method for you. Okay? Sometimes it builds things. Sometimes we draw things. Sometimes we write things. The method depends on the problem. Then you go to step 3. Now you go and use or analyze the method. Okay? So now, for example, you'd fill in the blanks. So you know you have this formula. So now fill in the answers. Plug numbers into the formula. Fill in a chart, etc. Make a rough draft if it's an essay. Look for patterns, right? You can work quicker if you can work out patterns. Sometimes you just kind of got to just dig in and do it, right? If you're building a fence, that's the problem. Sometimes you don't overthink it. You just start slapping the boards together and get it up, right? Trial and error. Sometimes it's just a trial and error process. But in step 3, just use your method. Now you got your solution, okay? Make sure your answer looks good. Go back to step 1 and go, okay, did my answer actually answer what I was proposing in step 1? Okay? If it is a math problem, okay, then that's what I've been trying to build with you, is techniques to get to the answer, right? That's the hope, if it's a math problem. Then the check, right? I mean, sometimes we just do this quickly in our head. You just look at a problem and go, yep, makes sense, and you move on. Sometimes if it's a bigger problem, you redo the problem, right? Just to make sure it fits. Sometimes you ask somebody else, hey, what'd you get on number 5? That's you checking it, right? Sometimes you check with the teacher, did I get it right? Okay? If you made a mistake, did you make a big mistake or was it just a minor mistake, right? So let's try it. Here's a non-math problem. Here's the problem. One day, a cab driver picks up 3 couples to take them to a dance. A girl's dressed in red, a girl's dressed in green, and a girl's dressed in blue. Then there's 3 boys who also wore the 3 different colors, red, green, and blue. So the 3 couples get to the dance and they're out dancing on the dance floor, and the boy in red dances with his partner, who's a female, over to the girl in green and says to the girl in green, isn't it weird, Mary? Not one of us is dancing with a partner dressed in the same color. So the problem is, given this information, what's the color of the girl in red wearing? That's the problem. This is not a math problem, but let's see if we can figure it out. using the 5-step process. Step 1, define the problem. This one's pretty easy. The problem is pretty well defined. We need to find out, by the time we get to step 4, what is the color of the partner of the girl in red wearing? So the girl in red, whoever she's dancing with, what color are they wearing? Okay, I think we got it. We're done step 1. We know what we're solving. Step 2, we need a method. Now, I don't have a math formula for this one, so I'm just going to draw out a chart. And I'm going to go, you know what? I'm going to list all the girls up here, all the boys over here, and then list all the colors. Red, green, blue, red, green, blue. I'm going to use this chart. All right. It's not the only way I could solve this problem, but that's the way I'm going to go with it. So now I move to step 3. Now that I have a method, I'm going to start filling out the chart. That's step 3. So I know that the boy in red is not dancing with the girl in green because that's who he talked to while he was dancing with somebody else. So there's no way that red boy could be dancing with green girl. She's out. I also know that red boy said not one of us is dancing with somebody of the same color. So red boy can't be dancing with the red girl, and vice versa. Green boy and green girl and blue boy and blue girl, they can't be dancing together. So I'm just going to X them out on the chart. Now more information starts to come to me, and I think, well, the only person left for red boy to dance with would be blue girl, right? These other two are out, so that's who he must be dancing with. Oh, and wait a minute. If blue girl's already dancing with somebody, she can't be dancing with green boy, so green boy's out. Oh, now wait. I also know that green girl, because there's nobody else left, must be dancing with the blue boy. And finally, because blue boy's already dancing with someone, he can't be dancing with red girl, so my answer comes out. The answer is that green boy must be dancing with the red girl. I didn't use math to solve this. I just used a chart and some logic, like I was talking about before, to come up with an answer. Because I want to know who they're dancing with. So when I get to step 4, I've got an answer. Green boy must be dancing with red girl. They must be dancing. That's all that's left on my chart. So I go to step 5, I check it. I go, does it make sense? Maybe I'd ask Solon, did that make sense to you? Yeah. Solon wakes up from his nap and he goes, yeah, whether or not he heard me or not, that's a different question. Now, just because I didn't make a mistake doesn't, by the way, prove I'm right. I've been to enough high school dances in 16 years to know that I made one major assumption in this problem. I assumed that the boys were dancing with the girls. But I've been to dances where girls dance with girls and boys dance with boys, and that's fine. So I assumed that all the boys were always dancing with all the girls, but it could have been a whole different mix. But you know what? I'm good to go. I've solved this problem. And that's what I want to do, is show you that 5 steps. In other words, if you slow down and think about things a little more clearly, you might be able to get through problem solving. Okay, so what happens when you solve problems? Well, 1, that's actually how you learn new things. By solving problems, if you didn't have problems, you wouldn't learn new things. 2, you get better at things. You practice things and improve what you have may already know. 3, you move ideas around inside your mind. So something that worked in one area, like say math class, might all of a sudden also work in some other area, like say science class, or even art class, or cooking class, or even hairstyling. Like all these things start to come together because you get better at things. As well, you now start to want to learn more. Your curiosity gets more up. In other words, simply put, solving problems is how we learn, and solving problems is how you basically work out for your brain. You know how to work out your body. You have to do physical activity to make your body stronger. To make your mind stronger, you solve problems. That's what you do. Okay, but you know what? Doesn't always work out that logic gives you the answer. And I'm about to tempt you guys with some stuff. I'm going to trick you. I'm going to be straight up with you. I'm about to trick you. Some of you are going to get tricked easily. Some of you won't. So in a second, you're going to see why. So if problem solving is working out your brain, sometimes we need to go beyond logic. Sometimes you can overthink things. Sometimes this can be described as lateral thinking or outside the box thinking. Let me give you an example. Here's a mental puzzle that's going to throw some of you off. Okay, get ready. Please don't share this with other people. I'm about to put something on the screen, and all I want you to do is read it out loud. Very simple, right? You ready?
We all read it out?
Yeah, read it out loud. Ready? Read it. Wrong. What's up there, in case you read it incorrectly, is Paris in the spring.
Oh, what?
That was an easy one, and I fooled most of you with that one.
What?
Paris in the spring.
Wow.
Why did you make a mistake?
You do it.
Because when you see one dot, you won't see the other dot because you're...
Did you overthink it?
Yeah.
Did you automatically fix it?
Yeah.
Yeah, you fixed it without me asking you to fix it. I didn't ask you to fix it. All right, let's try another one. Okay, so here's what's going to happen. I'm going to put up a bunch of words on the screen right now. They're in columns, okay? So I want you to start right here and read this first word and then go all the way down. They're not up here yet, but in a second they will be. When you get to the bottom, go to the next column and read it going down. And there's 4 columns of words. Out loud. You ready to read? But here's the catch. Read the color of the word, not the word itself. Go, fast.
Yellow, white, green, green, yellow, red, green, yellow, black.
The color of the word, not the word. Out loud. Say it out loud.
White, red,
Green, yellow.
red, green,
I
white,
mean
red, black.
Red, green, green, white, red. Oh my God.
Okay.
Red, black.
Green, red,
That's very
black,
confusing.
black.
Can I ask you a question? For those of you who did this out loud, it's important to do this out loud. It really is.
White, red, black. I did.
Generally, this may not apply to all of you, but generally what I find students do is they start slow. They'll go like yellow, black. No, I mean white, red. No, I mean green, right?
And then you think,
But by the final column, they've gotten quicker. And what I find most students tend to do is they tend to actually blur their eyes a little bit. Did anyone in here do that? Just sort of blur your eyes so you're not actually reading, you're just focusing on the color. What you did there was you trained yourself. Through a little bit of practice, by the time you got to the 4th column, you were faster because you developed a method of solving it. All right, the last one no one should be able to get. It's the most impossible problem yet. Ready? None of you should be able to read this paragraph. None of you. Because there's no words in the paragraph. Ready? Go ahead and try. Read it.
According to a research at Cambridge University, it doesn't matter what order the letters are the only important thing is that the first
and last letter be at the right place. The rest can be totally problem.
amazing, huh? Yeah.
Is because the human mind is not reading
What? That is
Okay, so none of you are able to read it, right?
no.
Were any of you able to read that?
Yeah.
Put up your hand if you were able to read that. All of you were able to read this? That's impossible. This is gibberish.
Makes total sense.
If I copied and pasted this into Microsoft Word, you know that little red squiggly line that comes under a... It would just be all squiggly lines.
It's amazing,
Where it's
because
all
that's
messed
actually
up, you
spelled right.
couldn't kind of add it up.
So in other words, you guys are smarter than computers?
Yeah.
Holy moly, give yourselves a pat on the back right now.
I can't because my
That's amazing. All right. So sometimes when you go beyond logic, you actually do better. Sometimes by not thinking too much, you do better. Sometimes you do worse when you overthink it too much. So my point is, logic is a good thing, but don't worry too much about it. Sometimes you're smarter or not smarter than even computers. So now, as we pull that back and now start looking at algebra, we'll start with the most important concept in algebra. And you've seen it before, and I'm putting it up there right now, the concept of a variable. Now, before I even move to the next slide, before I even do that, stop for 1 sec. Sure. And let me write down that word. And let's pretend we're not in math class and we're not in science class. Let's take that word and dissect it. Can you think of a word that comes out of this word? Very. Yeah. Yes, I did.
Able.
Sure. Able. Gotcha. Let's stop right there. Now, this word, what does it mean?
Many.
Many? Sure. It means many. If I say I'm going to vary the temperature in here, what does that mean?
You're going to turn it up.
Is that what it means? If I say I'm going to vary how much money I'm going to give you, if I was going to give you money. If I was your boss and I said, your paycheck's going to vary every week, what does that mean? It's not good? Is it just lower? Could it also get higher? No. To change, yeah. To many change. What does able mean? What does able mean? Able? What does able mean? To do. Yeah, to do something. If you're an able body, it means you're able to do stuff, right? If you're unable, then you can't do stuff. So basically, if we think of it that way, we're going to do stuff to change stuff. So a variable is really about change. Okay, let's go back into math world now. We're outside the math. We know what the word means. The word means being able to change stuff. Okay, now back to math. So we use language to communicate, obviously, and algebra is the language of mathematics. We'll get more into that in a minute, but hang on. If we use language to communicate and algebra is the language of mathematics, then variable is one of the most important things you can say when you're talking in algebra. And what a variable is it can represent different things. Oh, that's the change part. Now, when your teachers first taught you variables, they may have just jumped too quickly into using them without kind of explaining what they are. And what they are is something that changes. Okay? So it identifies a number that's not there and may not ever get there. Okay? It relies on the word varies or variable or vary. Okay? And in math, if we take out variables, then we're just dealing with numbers and symbols like this. But in some places, we don't need numbers. We need something to represent or symbolize a number that we don't know. So here's a piece of math using symbols. We don't know what the symbols are. Triangle plus square equals square plus square. Whatever that means. Let's see if we can figure out what it means. Well, if I replace the triangle with a 1, and I replace the square with a 2, I would write it out as 1 plus 1 plus 2 equals 2 plus 2. And that's true, right? 1 plus 1 is 2, 2 plus 2 is 4, and 2 plus 2 is 4. That makes sense. So a 1 could be a triangle, and a 2 could be a square, and it would work. But if I replace the triangle with a 2, and I replace the square with a 3, it becomes 2 plus 2 plus 3 equals 3 plus 3, and that's not true. Well, no, it would equal 7 equals 6, and that's not true. So what these things become is important. What they change into is important. Let me think of it another way. Think of a variable as a mailbox, right? You guys have mailboxes at your houses. But this is a special mailbox. It can only hold one thing at a time. It's really small. So in order to put something in the mailbox, if there's something already there, you have to replace it. So like, for example, I made you a really cool animation. This mailbox holds a 75. Oh, I want to put something else in. Then the 75 goes away, and then the new thing goes in. I know, it wasn't a cool animation. It was a boring animation. But. And that's what a mailbox is. It's a variable. It changes, just like your mail changes every day. Okay? But in math class, we don't want to draw mailboxes. We don't want to draw triangles. We don't want to draw squares, because it's not art class. So we need to use a symbol that's easy to write. And so, because we've already used up all the numbers, variables in math are letters. There they are. X plus y minus z. The letters represent things we don't know, but things that are going to change. Okay? Because you don't want to draw shapes. Shapes don't make sense anymore. Okay? But let's think of it this way. A variable is a package. It's a package of math stuff. Now, we've seen packages before. Packages, when I described them, was what brackets were. Brackages were packages. So are you saying that variables and brackets are the same thing? Kind of. What?
You said brackages.
No, brackets.
You said brackages.
I didn't, but that's okay. It's okay. Sure, brackages. But here's the thing. Remember when I said when we first learned brackets, I said they were like a Christmas present on Christmas morning. You want to open them up? Well, variables are like presents the day before Christmas. You're really excited about them because you don't know what's in them, but you can't open them. So 5 plus a present equals 7. We don't know what's in the present. Solving that is what algebra becomes, is solving that problem. There's your present. It's x. X is a letter to represent what it will become. Okay? That's what a variable is. It's this unknown package that we kind of have to unwrap and unravel. And it's going to change. Okay, so if that's the fundamental building block of algebra, what's algebra? Well, it's actually an Arabic word. The word algebra is Arabic, and it means the reunion of broken parts. That's what it means. That's what the word means. Now, does that sound very similar to something we were just doing? If you had a bunch of broken parts in front of you, what would be the thing you could do with a bunch of broken parts? Fix them, put them back together, right? Right? If you had 3 broken parts and you could put them back together, you would. You would solve the problem. So algebra, the reunion of broken parts, is really about solving a problem. Okay? It's putting real life problems into the language of math and then solving the puzzle. You don't normally start with algebra. You start with arithmetic. We've done that. Now we've come to the end of arithmetic. So now we need to actually use math to solve problems. Here's a simple problem. A clown was carrying a handful of balloons, and along came the wind and blew 8 of them away, leaving him with 9 balloons. So how many did he start with? Now, don't jump too quickly. Let's see if we can use algebra to approach this problem. Here's what we don't know. We don't know how many balloons the clown had. We have no idea. That's our unknown. That's our present that we need to unwrap. Here's what we do know. That 8 balloons were taken away. Now, do you know anything in math that represents taking something away? Is there a symbol we can use for that in math language? If I said 5 take away 2, what would you use? A minus symbol? Okay. So we know that there's 8, and we're left with 9. So what's left over is 9. So let's see if I could write it this way. That's the takeaway part. This is what we're left with. And this is the unknown. That's the amount of balloons he had at the start. Now it's algebra. It's a way we could solve for the puzzle. Now, I'm not going to solve it right now. You guys can solve it probably in your head right now, what the answer would be. Anyone got an answer? What is it? 17 minus 8 is 9?
Wow, I just got that as soon as you said it.
And there it is.
Literally
Okay?
figured out what that as soon as you said it.
But what students get confused by is they often just see the algebra. X minus 8 equals 9. But what the algebra actually is it's representing what you could do to solve problems. And by doing the algebra, you're getting better at solving the problems. All right, let's wrap it up. It's been a long class today. The takeaway for today is the following. These are the 2 words you need to know to start this unit. Algebra is the language of math used to solve problems. And a variable is a letter that represents something we don't know. The method I taught you of solving problems is a 5-step method. Define the problem, find a method, analyze the method, come up with a solution, check the solution. And that's it.